Welcome to the Latin American webinar on physics. I am Roberto Lineros from the Universidad Católica del Norte. And today we are in the webinar 180 of this webinar cycle in different topics of particle physics or astrophysics and so on. So in this opportunity, we have as a guest Adrian Thompson. He is currently a postdoc at the Northwestern University in the United States. Before that, he obtained his PhD from Texas A&M University, and before that, he obtained his bachelor degrees in physics from the UC Santa Cruz. So, Adrian, welcome to lawphysics. The webinar, the title of the webinar, sorry for the people, the title of the webinar of Adrian is the Terrestrial Neutrino Lighthouse. And now, yes, welcome to lawphysics, Adrian.
Awesome. Thank you so much. Yeah, thanks for having me.
You can start whenever you are
Okay,
ready.
cool. Let me share.
Mhm.
All right. So first of all, thank you so much for the invitation. I'm a longtime listener, first-time speaker in this webinar series. You had like amazing speakers that I've tuned into for a long time. So I'm really happy to be able to speak here. So my talk title is the Terrestrial Neutrino Lighthouse. In fact, actually, I wanted to name it just the Neutrino Lighthouse, but then I looked up, I found in the literature that the concept of a neutrino lighthouse already exists. These are astrophysical sources of neutrinos that I think have to do with compact objects or collapsing stars that have rotating accretion disks, and those spew out neutrinos at a sort of like a lighthouse, sending us beams of neutrinos. So this is not that. I'll talk about a terrestrial neutrino lighthouse on Earth and what you can do with it. And so I'll specifically talk about this recent work with Andre de Gouveia at Northwestern University, where we were actually asking another question about what you can do with high energy, high intensity neutrino beams for electroweak precision physics. So an alternative title could be something about electroweak precision with neutrino beams. Okay, so let me jump in with some motivation for this. Imagine that you are an electron sitting somewhere in a neutrino detector. Okay, let's say I'm this electron sitting here. And life is peaceful, it's quiet, everything's happy. And all of a sudden, you have this flux of neutrinos whizzing by you. And initially you get a little bit scared, but then you feel reassured because the neutrinos are ghostly particles, right? They don't tend to interact very often with normal matter. They have small cross sections, you think. But these are high energy neutrinos. These are like, let's say, hundreds of GeV to TeV neutrinos. And sometimes they do interact. And when they do, they can scatter off of electrons and rip this electron from its parent atom and send it careening through the detector, where it can then be measured and it's off to reconstruction. So this process is the so-called elastic neutrino electron scattering process. It was super important, dating back, since the early days of the development of electroweak theory, when people were first, writing down and trying to understand the standard model of electroweak symmetry breaking and weak interactions. And this process helped them think about how to actually test this electroweak picture, to test whether or not there's other gauge forces that are mediating the interaction between neutrinos and the rest of the standard model between the quarks and electrons. And it allows us to probe the weak force in kind of a unique way. So I can tell you about a couple nice properties that this scattering channel has. And the first property that it has is that it only happens via W and Z exchange at tree level. So of course, the neutrinos, at least according to them, they only interact with the weak interactions, right? They're not charged under color or electromagnetism, at least according to them. That's their alibi. They also told us, according to the standard model, that neutrinos are massless. That turned out not to be true. So if we want to sort of stress test this electroweak picture, this is a nice process to look at, specifically because our null hypothesis is that it only happens via W and Z exchange at leading order. And so in that sense, at leading order, you can say this is sort of like a purely weak process to study. And it allows you, in particular, to probe these weak charges that enter into the amplitude, the so-called G left and G right for some fermion F that show up in the standard model. These are dependent on the charges in the standard model, like the isospin and the electric charge, and the weak mixing angle, the sine squared theta W of the Weinberg angle or weak mixing angle. And so if you do an experiment where you look for this type of scattering process, that would allow you to measure these couplings and also measure the weak mixing angle in a way that complements other probes of the same couplings. Specifically, so what is the weak mixing angle, right? This describes how the photon and the Z boson are mixtures of their underlying hypercharge and isospin gauge bosons in the electroweak theory. And the weak mixing angle also runs, right? There's a renormalization group running description of the coupling that just expresses that as I go from low energies to high energies, I start being sensitive to the higher order corrections in the theory that are perturbing what I mean or what I actually measure when I say the weak mixing angle in my amplitude. And that's just expressing the fact that at high energies, I'm starting to become sensitive to the microscopic nature of this interaction and the way that it perturbs the tree level description of the mixing. And you can see that there's all these different probes. I've just shown like some of them here of some of the existing measurements at low energies. And they each have their advantages and disadvantages. They also each involve different gauge forces in the mediation or in the description of the processes that give rise to these measurements. For instance, you can look at this toy Venn diagram where you can see things like atomic parity violation involve both nuclear uncertainties, electromagnetism, and the weak force, while others like neutrino DIS, where you scatter neutrinos off of quarks embedded in the nucleus, involves knowing something about the strong force and measuring the weak force. And molar scattering, which involves both QED and the weak force, right? All of these different measurements of the weak mixing have their advantages and disadvantages. Some of them can be very precise, even in the face of being sort of embedded with these other gauge forces present in the amplitudes. Just to point out that the electron scattering process, so EVES, is somewhat unique in that it is insulated in some sense from strong force and electromagnetism. And it is a sort of purely weak measurement of these weak couplings, at least at leading order. And so we can use that to our advantage. That's the idea. Okay. So in that sense, it sort of makes for a good microscope of neutrino physics. But if you want to build a good microscope for studying the neutrinos, it would really help to have a flux of neutrinos that you understand super, super well. So one such flux would be coming from muon decays. We know muon decays super precisely to something like 1 part in a million. And they're also quote unquote purely weak at leading order. They only happen via W exchange. So if you were to come up with an experiment that combines the muon, anti-muon neutrino, electron neutrino, or anti-electron neutrino, muon neutrino fluxes coming from muon decay, with those fluxes coming, or with the scattering process of electron scattering, then this experiment would be at leading order purely weak and would also involve a flux that you understand really well. And it would be even better if the muons were decaying, if the muons, let's see. Okay. It would also really help if your muon flux was monoenergetic. Okay, and so we'll see an example of that. I'll motivate an example of this kind of setup. So this is the idea of the talk. We want to do electroweak precision with this type of flux and these scattering channels. Okay, so where can you do that? So I've sort of buried the lead here. I've sort of tried not to spoil what the talk is about, but where we can do this type of experiment is at a muon collider, or at some TeV-scale muon factory or neutrino factory. Okay, and this idea using neutrinos from a muon collider is not new. It's been a concept in the literature going back more than 20 years. And there's a lot of things we can take inspiration from, especially recently. There are things like the NuSong concept, which is not a muon collider, but is a concept to take on a number of different well-motivated physics targets using high energy, high intensity neutrino beams. And recently, there's been work on, for instance, the MAP designs and the International Muon Collider reports, where they have started just now to sort of crystallize the designs of some potential future muon collider or muon storage ring. Okay, and there's also things like the mu-Tristan design using mu plus beams. So there's a lot of things you can take inspiration from. And so that's the idea. We want to see if we can take a TeV scale muon storage ring or muon collider, use the neutrino beams to do precision physics. Okay. Of course, there's a lot of challenges with building a muon collider that you must have heard of. And the biggest challenge, or every challenge from the early stages of injecting the beam and creating the beam and cooling it to the detector side, all those challenges eventually wind back to the notion that the muons are decaying at any stage of this whole experiment. So every problem that you'll encounter eventually has to do with the fact that muons decay. And in particular, one of the backgrounds that people are not used to thinking about at colliders, like proton colliders or electron-positron colliders, are the so-called beam-induced backgrounds coming from the muons decaying themselves. Right? They release electrons in their decay. Those electrons scatter and rescatter and induce cascades of stuff all through the detector and the beamline. And so those are the so-called BIBs, the beam-induced backgrounds. But of course, the bibs also contain bins, the beam-induced neutrinos. So really, we can view this challenge as also somewhat of an opportunity, using the fact that all these muons in our beamline are going to be producing a high intense flux of neutrinos. And they're a component of our background, but they can also be treated as a signal, as something that you can use to do physics. Okay, and so this idea was explored very thoroughly in this very nice paper. You should really read this paper, The Neutrino Slice-At Muon Colliders, with Luc Lopez, Matheus Hostert, Carlos Arguelles, and Zhen Liu. And they investigated exactly how large these fluxes are by understanding the concept of this slice. So you can imagine, for example, if I have a collider ring, right, where I have mu plus and mu minus beams circulating and counter-circulating, as they decay, you sort of project slices or fluxes of neutrinos passing into your detector from both sides. And those can induce scatterings inside the detector volume through a number of different channels. And this plot on the left should give you a sense of how many channels there are. This is also just for the nu-E and nu-E bar cross sections. Obviously, you'll have a lot of charge current and neutral current scattering. These are basically like neutrino dinelastic scattering processes. There's the electron scattering processes. There's lots of stuff that you have access to, a lot of interesting channels that you can take advantage of. So that's the idea. We want to ask the question, what kind of physics targets can we get from a neutrino flux like this? Okay, and in particular, well, I should say actually, the challenge here, of course, is that the beam-induced neutrinos, the bins, will be relatively small compared to the bibs, just the normal backgrounds from electron decays and everything else. So doing neutrino physics in an environment like this might be a little busy. It's actually kind of an open question as to whether or not we can actually handle an environment like this if you want to do precision neutrino physics. But we can use something to our advantage, which is the fact that these muons are super high energies, like let's say TeV-scale. That means that their divergence of the daughter neutrinos as they're from their decays will be very, very small. They will be very collinear and very collimated. For example, if you look at the neutrino flux coming from, let's say, 500 GeV muon decays, here's the flux, the differential flux on the y-axis, for a variety of different energy fractions of the daughter neutrinos. Their maximum angular divergence is going to be sub-milliradian. And if you go up to 5 TeV, it's even sub 0.1 milliradian. So that's super collimated. That means, even a couple hundred meters away from the beam line, my neutrinos are going to be collimated in a beam spot that's maybe order centimeters to order meters at a kilometer away. And so you can use that to your advantage and maybe think about putting detectors slightly away from the beam line, away from the high radiation fluence of visible particles, but not too far away so that you can catch a lot of the neutrinos. And so this is basically the lighthouse concept, right? Imagine this is your, a cartoon of your collider ring. I have a muon bunch that's circulating. As that muon bunch is circulating, it will stochastically decay to neutrinos. And you can imagine a beam spot of those neutrinos showing up at some imaginary surface some distance away from the collider in the plane of the collider ring. And as my muon bunch goes around, I could think about putting a detector somewhere here that would catch that beam spot and see flashes every time one of those bunches cross, or whenever neutrino decays will stochastically happen from the bunch. Okay, so this is the sort of lighthouse, the neutrino lighthouse that you can build on Earth. In terms of numbers, what we want to ask now is like, how many neutrinos do you actually catch with this? What is the intensity of the flux? A few numbers just to keep in mind to sort of put things in perspective. The nominal bunch intensity, for instance, at the IMCC design is something like 10 to the 12 muons per bunch. And the circulation rate is close to speed of light for, let's say, a 10-kilometer circumference ring. That gives you a 30 kilohertz circulation rate or so. And so now we want to ask, okay, what is the actual acceptance? So our basic idea is, again, let's take another view. I don't know what the actual design of my muon collider is for this study. There may be a number of different stages and acceleration stage rings and then a final collider ring. But let's just focus on this collider ring and again think about our muons circulating and counter-circulating. Those muon decays will shoot neutrinos off like this. And so the idea is that I want to put a detector over here. Okay, somewhere off of the ring, not too far away, but not too close, so I don't get a lot of radiation influence. So why did I put a hockey puck here? I put a hockey puck just to suggest the fact that, again, these muon decays will be very columnated, so I don't really need a super tall detector. I can have, a detector sitting in the plane of my collider ring that doesn't have to be too tall. It can be kind of short or shallow, maybe like a meter high or something. Because again, that neutrino beam spot, let's say 100 meters away from the edge of the ring is, order centimeters. But I would want a wide detector, something like a wide and shallow or short cylinder, like a hockey puck, so that I can catch all the high energy leptons that I'm going to get out of the neutrino scatterings in my detector. And if I want to do things like DIS too, where I get like hadron showers, I would want to contain that completely. So I want a really broad, but maybe a shallow detector. So I don't have to use too much volume. Okay. I also want to give you the impression that because we are putting our detector somewhere outside the ring like this, we may get fluxes from both the mu plus decay and the mu minus decay in such a way where if your detector has direction reconstruction, then you can tell the difference between these two fluxes. On the one side, you'll have, let's say, mu minus decays going to nu mu and nu e bar, and you can separate those from the combined nu e and nu mu bar fluxes on the other side. And for instance, here are some toy plots showing you the angle of entrance into your detector, sort of lying along the plane of the muon ring. And on the y-axis, you're seeing the size of the beam spot in the vertical direction where x is pointing out of the plane of the ring. And so again, these can be contained. Here, I think we took a 4.5 kilometer circumference. These beam spots can be contained, within tens of centimeters at most. Okay. So that's a nice opportunity. Okay, so now we can ask what is the actual fraction of useful muon decays that we can make use of. And by that, I mean, how many muons as they're circulating in the ring, let's say you have n muons that will eventually decay in your ring over some period of time, how many of those actually lead to neutrinos that will pass into the fiducial volume of your detector? So let's say our detector is here with the width W, and it's some distance d away from the center of the collider. You could argue by geometry that the number or the fraction of useful muons is something like W, the detector width, over 2 pi d. And so then you would just multiply that by the number of muon decays that actually happen over some exposure, and that gives you the number of neutrinos. And if we can just put in some numbers, so for example, think about like a 10-kilometer circumference ring. So that's a radius of 1.6 kilometers or so. Let me put my detector distance d equals 1.7 away. In other words, this difference from the edge is like 100 meters. Okay, so I'm well away from the background radiation influence of the bibs. And I'll take a 20-meter wide detector, so something that's chunky and big, but not crazy big. I don't need to take something ridiculous. From that, you will get a fraction of useful muon decays of around 0.2%. And using some nominal figures from the literature, let's say you have order 10 to the 20 muons per year in the ring. Over a 10-year run, then you get something like 10 to the 18 neutrinos in your detector volume over those 10 years. And so what we'll do in this study, given that designs are constantly evolving, and we have maybe a couple different designs that are sort of being talked about and thought about right now, what we'll do is just fix these numbers as a given, and then ask the question, how much sensitivity could we get with this flux at various energy benchmarks, like a sub-TeV machine, so muon energies of 250 GeV up to 1.5 and 5 TeV. Okay. The other thing I want to be totally agnostic to right now is what the detector technology is. So for now, I'm just going to assume that the detector has some nominal electron density. If your detector doesn't have electrons in it, then there's other problems you have to deal with, but we're not going to think about it right now. So all I know is that my detector has some electrons. But we would obviously like, things like charge identification would be great. Good timing, all these things are sort of things we can think about later. Okay. So I should also mention that using the curved sections of the ring to get your neutrino flux, that's not the only option. I know in the past people have talked about these so-called racetrack designs, like the one I'm showing on the right. And of course, in the realistic muon collider design, you can look up some of these sketches of what the planned rings would look like. They will have straight sections, most likely in the vicinity of where they want to turn the muon beams to actually meet at the collision point. And so you can think about using those straight sections instead of the curved sections to integrate more and more flux. And you can think about putting detectors, let's say, on the opposite sides of the straight section, where this one integrates, for example, a lot of the flux from the mu plus beam, and the other one can integrate a lot of flux from the mu minus beam. So there's multiple options on the table, but for now we'll just remain agnostic to that and assume that we have some high intensity neutrino flux that we can make use of. All right, so going back to what we want to study electron scattering. Okay, so this slide has lots of mathematical details, but just want to flag a few things. So here are the cross sections that we want to study. These are the tree level cross sections for the EVES process or electron scattering. For now, we're going to do things just at tree level. And we can ask how sensitive are we to the weak couplings that enter into the cross section, the left and right couplings that enter in for the antineutrino cross section and the neutrino cross sections here for flavors alpha. And you can see how the dependence, the cross sections will depend on those underlying couplings that are involved in the effective GL and GR that I've written down here. And the second thing we can do is imagine just fixing sine squared theta W to some typical momentum transfer scale of the experiment. And so I'll sort of put off for now thinking about how the running plays a role. For now, we just want to ask what is the sensitivity to the overall couplings. And we can write down the interaction rates in our detector. That's going to go like something, the number of muons that decay in the runtime that we're interested in, times the fraction of useful muons that I wrote down, times the number density times detector length, and then I just convolve the muon decay flux with my cross section, and that'll give me my event rate. Okay. A nice thing that you can see from that is if you overlay your event spectra as a function of the momentum transfer. So I wrote down those cross sections in terms of the recoil energy of the outgoing electron, but I can trade that recoil energy for the momentum transfer scale in the experiment on an event by event basis. And so if you overlay those spectra over the running of the weak mixing, you can kind of get a sense that you'll be aware of where you'll probe the weak mixing angle as a function of Q. For instance, in these dotted histograms, these are for the sub-TeV machine. Those peak at around 0.2 GeV. But as I move to higher energies for my muon collider up to a 5 TeV beam or 10 TeV center of mass energy, that peaks at like a GeV. So you can see that as I go to higher energies, I sort of roll over this shoulder of the weak mixing angle, and I can start to probe parts of the parameter space, sort of neighboring, for instance, this NuTeV anomaly that has been kind of hanging around now for some time. So it's an interesting part of the parameter space to probe. You're probing the sort of the low energy behavior where you first start to see momentum dependence in the running of the mixing angle. Okay. We can also look at some rates. So just to give you a sense of how much statistics you have, at these energies, the cross sections, are higher than what we're used to dealing with, like with solar neutrinos and reactor neutrinos undergoing electron scattering. You have something on the order of 10, billion events in each of these channels. for the benchmark fluxes that I've assumed. Okay, so that's a lot of statistics. Naively, and now I don't know what the duty factor of the collider will be, but naively, those event rates could be large. That's like one event every 30 seconds for electron scattering. But of course, neutrino DIS, charge current neutral current scattering, can be much, is 1,000 times bigger cross section. So that could be a much more active event rate that you have to deal with. So I think detector timing capability is something that you want to think about. Of course, you can also ask if that's a background for us. So the signal that we're interested in is just a single electron that's undergone this elastic scattering. But other processes can create electrons in the final state. Those, if they're mostly coming from charge current and neutral current scattering, those would also be associated with lots of hadronic activity. So I'd imagine that it would be very easy to sort of remove those backgrounds to the signal that we're interested in. But I can imagine situations where, like, if some of those hadronic jets are produced near the edges of the detector, then they can leave a single electron track inside, and maybe that would fake your signal. But I think that could probably be solved with a fiducial volume cut. It's something that we probably need to think about more, in addition to things like energy resolution. Okay. So for now, we'll just assume everything is background free and super idealized. And what we want to do is just a simple chi-square test. And again, we can consider a couple different scenarios. One where I really have a muon collider with equal mu plus and mu minus fluxes, neutrino fluxes, and I can use both of those in my analysis with separate chi-squareds built for the mu plus flux coming from one direction and the mu minus flux coming from the other direction. I can also consider a case, like for instance in the mu-Tristan design, where maybe I only have one of the signed muons in my storage ring, and so I could consider the mu plus flux by itself. And for now, let's just look at sensitivity to the effective couplings that enter into the cross-section. And just to put them in a better framing to compare with existing literature, I'm going to rotate these left and right couplings into the vector and axial vector couplings, just so I can compare with existing constraints. And as I mentioned, we're also going to imagine fixing the momentum transfer scale for sine squared theta w to just some average value for simplicity for now. Okay. And so this is what you get. So this is kind of a complicated plot, but I can walk you through it. The overall panel here is showing the sensitivity to the axial vector coupling against the vector coupling. And in the big panel, these lines, the brown lines, are constraints from things like LS&D, and purple, Texano, reactor experiment. You have another constraint from CHARM 2. Okay. And if I zoom in here, this is the sensitivity that you get from our projections for the muon collider or muon storage ring. And if we zoom into that, then you can see sensitivity for the combination of using both mu plus and mu minus beams, where that information actually breaks a kind of degeneracy in the correlation of the couplings. That's why you get sort of a flat ellipse. But if I only use one sign, like a single sign storage ring for only one of the fluxes, then I'll get some sort of correlation or degeneracy among the two couplings. But in either case, you get really, really good precision. At the best case, you get something like 0.05% precision for the 5T EV machine. So this is going to be at the sub% level. Okay. So we can ask more detailed questions. We can ask more like an in-depth question about these couplings. Let's say we break the assumption that they are flavor blind couplings. For instance, again, I can imagine fixing sine squared theta w to some average value based on the average q squared. But I can promote my left and right couplings to flavor dependent couplings, where I can say now the left-handed couplings to the neutrinos now come in the flavorful GL nu E couplings and GL nu mu couplings that would be entering into the cross-section for the separate components of the flux. And that's a good way to test flavor dependence at higher orders. This is sort of a proxy for that. And you can also see what the sensitivity to that sort of test hypothesis is. If we want to test how flavor blind is the standard model, at least at leading order. And again, you can get similar sensitivities. And you also have this degeneracy or correlation that shows up and that is more pronounced for the single sign muon storage ring. But you can break that a little bit with a mu plus mu minus collider where you're getting both fluxes in the detector. And again, you're going to sub% level precision for that. And then there's other things you can imagine testing. So if we're getting this level of precision, you can then ask, what about higher order effects in the standard model or in the I can ask about neutrino scattering at NLO at next to leading order. And one of the observables that you can think about is the neutrino charge radius, which enters in as sort of an effective operator that comes from single or photon exchange with the electron at one loop. And this process is also flavor dependent. And you can write down the charge radii as basically the second moments of these form factors that enter into the effective loop correction. Okay. And what that eventually amounts to, if you put all that in and add this correction into the cross section, it just turns into a translation of the left and right couplings that I wrote down. A translation proportional to mw squared, and in the standard model, the charge radii of the neutrinos is going to be proportional to G Fermi with some log factors, depending on the lepton that you are, the flavor of the neutrino that you're asking about. And so we can do a similar test where we pretend that there is no charge radius contribution to our null hypothesis, to our data, our fake data. And we can ask what the sensitivity is. Whoops. We can ask what the sensitivity is in the space of the electron neutrino charge radius and the muon neutrino charge radius. And you can see that as I go from the sub-TeV machine in blue to the 1.5 and 5 TeV machines, those can get sensitivity below the point where we would expect the standard model contribution to the charge radii would start to show up. In other words, we would be sensitive to that level of a correction. And this fact has nothing to do with the energy scales. It's more to do with the high statistics that you get at higher energies, just because the cross section is growing. Because the charge radius itself is not necessarily, it's a energy independent contribution to the couplings that you're probing. Okay. All right. So, and I guess I also want to mention here that, in principle, all these NLO effects should probably be taken together. If I want to make these measurements, I should probably account for the running of the coupling, the charge radii, and there are more NLO effects that that can happen. And for instance, you can see some of these references here that talk about those things. Okay. So what about the running of the weak mixing angle? Can we actually tell from this data that the weak mixing angle is running in our data set? And the answer seems to be yes. You can test that in a really naive way. A toy model is to say, let me take those left and right couplings that enter into my cross-section and promote them to momentum-dependent couplings as a function of the running of sine squared theta w. So I can take the running of the coupling from some standard results in the literature, inject that into my cross-section, and see what the difference is from the hypothesis that the running is just, or the weak mixing angle is just fixed to some value. And so that's what these plots are showing. I'm showing the event spectra as a function of momentum transfer for the mu minus beam and the mu plus beam on the right. And on the bottom panels, I'm showing the subtraction away from some fixed sine squared theta w hypothesis. So in each bin, I'm basically subtracting the event rate that you get if you fix sine squared theta w to some value at an average momentum transfer from the event rate that you get with the running included. And you can see that there's a systematic sort of wavy behavior in the data that you would be able to pick up. And it's different also for both the mu plus and the mu minus beams. And it tends to show up, of course, at higher Qs because that's where you start to sort of roll into the shoulder of sine squared theta w. This subtraction was also done at the average momentum transfer. So in some sense, this is like the minimal difference that you could achieve. If I picked some different momentum transfer hypothesis for the fixed sine squared theta w, this systematic shift would get bigger. Okay, and so here's one way to test that. What you can do is, again, you can take the spectra that I get, let's say from the muon collider, I have the nu e bar, nu mu, nu e, and nu mu bar fluxes. And for instance, if I look at this far left panel, I can show the spectra as a function of Q, and I can chunk my data into 4 regions of momentum transfer. I'll just call them regions 1, 2, 3, and 4. And I'll build chi-squareds in each of those regions. And in each region, I'll separately extract a fixed sine squared theta w from a fixed hypothesis, test hypothesis. And you can see the results of those extractions in the bottom panels. For the sub-TeV machine, you can see the error bars in each of those regions. And for that sub-TeV machine, just looking at the size of these error bars, you can kind of see that there is a little bit of momentum dependence. But I can also fit a straight line through these error bars, and I might get a decent enough fit. In other words, I might not be able to prove that sine squared theta W is indeed running. But as I go to higher energies, if I go to the 1.5 TeV machine or the 5 TeV machine, the error bars are shrinking, and it's abundantly clear that yes, you are seeing the running present in the data. And so you can imagine doing that straight line testing would probably not give you a very good fit. Okay. And we can kind of compare that with existing data. So I have a potentially incomplete set of existing measurements on the running of the coupling here. Again, I mentioned things like APV. There's also coherent scattering. There's the E158, electron DIS, et cetera. There's the collider measurements at high momentum transfer. And we can overlay some of the future projections on this space. Again, this is also an incomplete list, but there will be lots of more information on the low energy side from things like reactors and more from spallation sources, coherent scattering, molar and P2, like future molar scattering experiments. Solid and the electron ion collider, for instance, will be able to constrain and test this running of the coupling at high momentum transfer. And now if we compare that with what the muon collider can say, again, in this idealized case, the sub-TeV machine would look kind of like this, doing poorly in the low energy regime, again, because you're just running out of statistics, but doing quite well already at high Q squared going into the just below the sub-GeV momentum transfer range. And as I move the collider energy up to 1.5 TeV and to 5 TeV, you can start to see how I'm rolling over that shoulder. And now I have like a complete landscape of measurements over this whole space. So I'm testing the entire running all the way up to the Z-pole. And so that would be very nice. Here's another plot showing all the three benchmarks that I considered combined, but it's probably too much information to look at in one plot. So, but you can stare at it if you like. Yeah. So that was this method was like, this is one method that you can use to estimate your sensitivity to the weak mixing angle running, but there's another way that you can do it. For instance, you can think about instead of chunking your data into those four regions, I can take all of my data, but make some affine test hypothesis for the functional form of sine squared theta W. So for instance, let me say that my weak mixing angle running should go like some constant plus some first derivative term expanded around some average momentum transfer Q naught, let's say. Okay, I'll call those constants A and B, but they can be stand-ins for the measurement of the weak mixing angle at some Q naught that I pick and the derivatives about that average momentum transfer. And I can do the same test in this space of the derivative coefficient versus the constant coefficient. And you can see in the sub-TeV machine, I can't quite rule out the B equals 0 hypothesis. In other words, this line at B equals 0 is reflecting the hypothesis that there is no running in sine squared theta W. So I can get a fit that's consistent with that. But as I move to higher energies, I can no longer, I would rule out that part of the null hypothesis. And so I definitely see the running at several sigma away from B equals 0. Okay. This is kind of a useful way of framing it too, because doing this kind of experiment is cool in its own right, I think. I mean, you're seeing the physical running of a coupling within a single data set of a single experimental configuration. That's also kind of just reflecting the fact that you're doing neutrino scattering at NLO, and you're seeing the momentum dependence start to kick into your event rate. But it could be also useful if you want to start thinking about new physics. There are proposals to look at the running of the coupling to high scrutiny, where you can imagine new gauge forces like Z primes that can enter into the NLO description and perturb this running of the coupling. For instance, like these papers by Marciano and Serlin, Singer, Davidiassel et al., where you can get systematic shifts in the running or little perturbations. And so framing it in terms of measurements on the derivative and the constant term and maybe even higher order derivatives if you want, that could give you a handle on constraining those types of new physics contributions. Okay. Okay, so I'm probably going a little fast, but that's okay. I just have a few more things to say. We also thought about a number of other things that you can do with this type of machine. There's like a lot. I mean, you can, if you're doing this level of precision neutrino physics, there's a lot of other things that you consider that I didn't mention. One of them that's pretty interesting is the fact that you also have tau leptons being produced inside the detector. So this is happening through the so-called induced lepton decay processes. It's an analog of the same anti-electron scattering that you have in the S channel, except instead of producing an anti-electron neutrino and an electron in the final state, this W can produce an anti-tau neutrino and a tau, or an anti-mu and a mu. And if you estimate the rate from these so-called induced lepton decays, you get something like 10 to the 4 taus in your detector using the flux benchmarks that we assumed. And so that's being shown in the green histogram where I'm showing the electron spectrum, the final state tau energy spectrum in the green histogram. And so you can use that for a number of things. I mean, people like measuring tau decays to constrain a number of different new physics operators. For instance, I can think about flavor non-universal operators that could change the way tau decays happen in the neutrino flavor space. For instance, when I'm doing this experiment, I know from muon decay, that these electron neutrinos, I know what my flux is from muon decay very well. And I also know their polarization very well. But I don't necessarily know the flavor of the outgoing neutrino in this scattering process. And if I measure this scattering process and look for the decay of the tau, I can constrain sort of a flavor non-universal operators like this by sort of measuring those processes. All right. So probably there's more to say, but I'll kind of stop here. I want to leave you with this take-home message. So clearly, a muon collider, if they can actually build it, there are a lot of challenges. There's many things you can do with it, right? You can use it as a Higgs factory and put the Higgs under a microscope in some sense. You have vector boson fusion that you can look at. You can look for BSM at the TeV scale. You can do lots of things. But this machine is also a neutrino factory for free. So why not use that? And you can put the neutrino under a microscope by doing things like these electroweak precision experiments that I was talking about. Okay. And there's a lot of future work, though. I mean, there's things that I didn't talk about, like the beam polarization. So if you go back and look at that neutrino slice paper, they will show you that the beam polarization can modify the event spectra of your neutrinos in a substantial way. And so you can start thinking about that and how it affects your sensitivity and what things you can do with that. Other things, as the design of these machines evolves, will play a role, like the beam profile and whether or not they're the so-called wigglers, which will sort of wiggle the beam flux to spread out the radiation fluence so that it's not so bad, and seeing how that wiggler will change the profile of the neutrino flux and its divergence. If we do, propose this companion neutrino detector some ways away from the ring edge, then you can start to think about all those things that I kind of glossed over, like the detector optimization, the location optimization, its timing capabilities, reconstructing capabilities, charge identification, all those kinds of fun things. And there's a lot of like physics targets that you can think of. Another one that I didn't mention is neutrino tridents. So that's the 2 to 4 scattering where you're producing lepton anti-lepton pairs from the neutrino scattering. That also depends on the weak couplings, and people have used that or proposed that as a channel at future experiments like DUNE and other neutrino factories to break degeneracies in the weak couplings between that and electron scattering. So I didn't show it in the plot that I had a few slides back, but there's this fourfold degeneracy in the weak couplings that you can start to break with channels like that. Of course, there's the inverse tau decay and inverse muon decay channels that I mentioned. Those are cool. There's lots of other cool channels that I showed from the neutrino slice paper. And of course, you can look at charge current or neutral current deep inelastic scattering as a direct probe of the so-called NuTeV anomaly. That would be a direct probe, but you can also use this electron scattering as sort of a complementary, purely weak probe of the weak interactions. And of course, there's lots of BSM targets you can think about. The new gauge forces entering into the running, neutrino NSI, heavy neutral leptons, and the general next to leading order description and radiative corrections of neutrino scattering. So lots of fun stuff. We're continuing to think about this. It's sort of an evolving picture. But yeah, I think that's all I want to say. So yeah, thank you very much. I'll take questions, please. Okay.
Thank you very much, Adrian, for the super nice talk. It was I like it a lot.
Thanks.
So we can start with some questions. I don't know if Carla.
Hello.
Hi.
Thanks for the talk. This was very nice. My connection was really bad today, so it was cutting a lot. So I start asking. Sorry if you mentioned,
Oh,
but
okay.
I'm curious about detectors. In the sense, if you have an idea which kind of detector you could place there, which signature. And then the question is if you take into account the detection uncertainties in your predictions.
Mm-hmm. Absolutely, yes. So we've started talking about this, and from the detector folks that I've talked to, like for instance, we actually had Dr. Ben Rosser from U Chicago come and visit us at Northwestern recently. He worked on like the Maya design for the detector apparatus in the vicinity of the collision point. And some of the things that we've been able to realize is that you probably don't want certain detector technologies that might have slow timing. It's my understanding that things like liquid argon TPCs that are super popular now for like the neutrino factories of today, those might be a little slow for the things you want to do, but that might also depend on the distance from the beam, if it's a really, really active source or less active. So the suggestion of just using something similar to the detector technology in the at the collision point, like electromagnetic calorimeters, maybe even trackers, that could be something I could see happening. Yeah.
I see.
Yeah.
Okay, thanks.
Yeah, of course.
Thank you, Carla. So I have a questions, three questions, let's say. One is when you were talking about the muon ring, the beam of neutrino is expected to be, because I didn't get so well. It's expected to go through, let's say, air, or it's in principle could be through matter. Let's say I know that the distance with the detector is short, but
Mhm.
my question is related because of the background. If is it passing through something that could trigger other pion production or something like that? Because
I see. Yeah, most likely. I think that's right. I mean, I would imagine that right after or right around the beam line, you would have like, maybe some shielding and rock. And then between our proposed, companion detector and the beam line, it would be mostly like dirt and rock. Uh, so that's a good question because, yeah, as the neutrinos are propagating, these are high energies, so they don't attenuate very much over distances of only 100 meters, but they do have high scattering rates. So you could imagine like background stuff being created from neutrino scattering in the rock, around the detector. Absolutely, yeah. And I can also imagine things like, electrons or hadrons leaving the rock and penetrating into your detector apparatus. So thinking about maybe, more shielding and vetoes and stuff like that probably would be a good idea. That's my guess, at least. Yeah, it's a good question.
okay, thanks.
Yeah.
So I have another question, but we got a question from the YouTube channel. His name is False6. Say he's asking or she's asking, can you outline how a Z prime can affect the running of the intermediate energies and not be seen as in left slack either via sine theta square or direct searches of Z prime
Okay. Yeah,
experimental?
that's a very good question. I have one backup slide. It's not a very good backup slide. It just has one plot. So I'll point you, and there must be other references that you can probably find, but I'll point you, for instance, to this paper from 2023 that explored these types of issues. The basic idea, from what I recall, is that you have a Z prime with a kinetic mixing and a gauge coupling and a mass. And those three parameters can, in that parameter space, you can explore how it perturbs the weak mixing angle in this way. And in this specific example, for the setup that these authors considered, it results in a sort of gentle lifting up at low energies. In terms of constraints from other things, I probably should look into this paper a little bit more carefully, but I also have the same question. It might be really nice to have a plot where you can show constraints on the Z prime, maybe in terms of its gauge coupling and its mass for an assumed kinetic mixing, and show that landscape of constraints in conjunction with the sensitivity you can get from looking for things like this. I'm not sure if that exists, but maybe someone has written a paper about it. So yeah, that's also a really good question. I'm not too sure.
Okay, thanks for the answer, and for say that to if he want to continue asking other questions, he can write it in the chat. So I have the question that I wanted to ask before. What about, because with this sensitivity, is it possible to try to indirect estimate some neutrino mass mechanism for the? I mean, I know that the neutrino mass value is impossible to measure in this experiment, but at least the couplings in some of these theoretical models that can provide some mechanisms for the neutrino mass generation, like a one loop generation of neutrino masses or something like that. I don't know.
Yeah, I think so. My guess is yes, you should be sensitive. I could imagine sensitivity coming through like considering extra mediators in the scattering that might be part of of UV completion that is responsible for the generation of the neutrino masses. Um, maybe because this momentum transfer is at somewhat high energies, it's not quite at the level of the weak scale. So if your mediators are like more than hundreds of GeV to TeV, this would still look like just a heavy NSI in the detector. But you would still get sensitivity to that part of the parameter space, and I think you can indirectly probe models that might lead to some modification of the scattering in that limit. Yeah, and of course things like HNLs, I can also imagine doing studies looking for HNLs that might be part of, let's say, like a B minus L setup for the explanation of the neutrino masses. But I'm not sure how hard, like how high the reach would be in terms of mass reach to the new physics scale. That would be a cool thing to explore.
Cool. So, and I have another question more, but it's here in the same slide. This the rising of the value of sine squared theta w. Is there any experiment to can be? I mean, for high Q, you have this
Oh,
value.
Yeah.
Because the lowest is LHC and left. You put in the slide 37, I guess. There are the.
Right.
Is it possible to observe what happened after that with some experiments, or it's too high in the?
I think I have a feeling that the points that I put on this plot are incomplete. I'm sure if you look at the literature, there must be some projections for measuring Qs higher than the z-pole. I'm not sure where they are. I would also imagine you get similar sensitivity from the muon collider itself, from the mu plus mu minus collisions. So there must be a way to start probing this high Q region.
I was wondering maybe the interplay with this neutrino observatory like IceCube, because those also are very high energy neutrinos. If they can kind of.
Actually, yeah, that's right. So they must right. Those must have momentum transfers that are ridiculous. So probably, yeah, I should look that up. It's probably out here somewhere. Yeah, I would think so.
Yeah, that's true. And maybe the interplay with the muon ring. So yeah, I guess you mentioned also, but just I don't know if there are other questions on that. But what about the because you just mentioned the heavy lepton. It's possible to also to have some deviation because of production of a not heavy lepton, but maybe a fourth neutrino that is still couples but is kind of sterile or something like that that you can still produce in some way.
Mhm. I think, yeah, that you could certainly get into that. This would likely have to happen from the mixing after the neutrinos are produced. You could also, in principle, think of modifying muon decay itself, but that we already sort of constrain the muon lifetime so well that there may not be a lot of room for new physics in the decay itself. But I could definitely imagine probing like mixing parameters once the neutrinos are produced, and you can mix into some heavy neutral lepton state. Um, there's also things like what we learned from fixed target experiments, like the SBN program and Dune. You can use all of the secondaries that are produced in like the beam targets, like all the electron positrons that are being transported through the beam target to produce long-lived particles and Z primes through things like Bremsstrahlung. And I think you would also have some of that here. I don't know how intense it would be, but all the beam-induced backgrounds will eventually scatter with something. A lot of them will scatter with absorbers, like conical absorbers that they'll put in the vicinity of the collision point. So I could also imagine doing like a beam dump style experiment that you're getting out of this as well, where you can maybe look for Z primes, and then those Z primes could decay to H and Ls. Yeah, there's probably a number of different scenarios people can look into. Yeah, yeah.
Cool. So I don't know if Carla, if you have another question for Adrian. No. So I guess for the
Oh,
cool.
thanks.
I guess for the time also it's gonna be almost 1 hour for the transmission. So first of all, thank you very much, Adrian, for your talk. Was very interesting and will be useful for the future viewers of the Law Physics YouTube channel. And if for all the people that are following us in the transmission and in the social networks, you can see all the previous webinars that we have here in this series, and also to subscribe to the channel to not lose the latest news about which is the following webinar. In fact, the next webinar is going to be in 2 weeks. Yes, 2 weeks, and it's going to be Amitaius Banik. So just to tell to the people to stay tuned to Law Physics, and we will see each other in a next opportunity. Thank you, Adrian, again for the webinar. Very interesting and very useful also for PhD students and postdoc that they will watch it.
Awesome.
So
Thank you so much. Yeah, thanks for the invitation. I appreciate it.
okay, see you all.
Thank you.
See you in the next opportunity. Bye
Thanks.
bye.
Bye. Thanks.
Okay, I stopped the transmission.
Okay.
Very interesting.